up where we left off. We had factored, we had canceled, which meant there was a hole at that point because something canceled. We had found the domain, so that was reading our graph left to right and looking at, there was a break at the vertical asymptote, there's a break at the hole, and those places are breaks in the domain. Range. In terms of range, we're going to think
Up and down. Y.
up and down. It's the y's. So we want to read in terms of start low and work your way up. Okay. How low does my graph go?
Negative infinity.
Okay, it's going down to negative infinity. And where's it as we're moving up? Where's the first break in the y values?
Oh yeah. The asymptote. The 5/3, right?
Mm-hmm. So before there's going to be a break at the asymptote, but before that, there's a break at the hole. Yes? Okay. So while yes, we're going to start down at negative infinity, that first break we have is at the hole. What did we already find the ordered pair to be at the hole? Yeah, we already found that to be the ordered pair, 3, 5/3. And so the y value this break happens at is 5/3. 5/3 is going to have a parenthesis. That value is not included because it's a hole. Where does my graph restart? Other side of 5/3. And where's the next break in y values? Okay, the horizontal asymptote. So that graph, even though it looks like it barely goes past 2, we realize it's going to keep going up and up and up and getting closer to 3. So 5/3 to 3. 3 with a parenthesis. Where does my graph restart? Above 3. Yeah, it's over on the left side, but in terms of y values, that's a 3 with a parenthesis, of course. And then next break. Yeah, it's going infinitely up. So positive infinity. Okay. Vertical asymptote. Where's the vertical asymptote?
Negative.
Okay. If we write the equation for that, okay, vertical asymptotes are x equals. Vertical lines are x equals because they cross through the x-axis. And so, did I say I hope I said -3, but I wrote it. So x equals -3. Now, we have the graph to look at. How do we know there's a vertical asymptote? Looking at the equation. Those cancel, which created the hole, and what remains? The x plus 3, which when you set it equal to 0 means there's going to be a vertical asymptote at x equals -3. Okay. When I rewrote today, I didn't write on here, but when we talked yesterday, we talked about the hole being a discontinuity, yes? And you guys have that written on yours. I just, didn't get it written on here. Point discontinuity, it can be called a point discontinuity, which you're going to see that in homework in this, in this calculus. So I want that, but it can be point discontinuity, or what you're more familiar with is removable. You'll see both in this calculus curriculum. Now, a vertical asymptote is also a discontinuity. This one, though, what kind of discontinuity do you know it as? If we knew holes as removable, vertical asymptotes were non-removable, is what you probably knew it as. So you could say a non-removable discontinuity. Calculus also talks about it being an infinite discontinuity. Maybe shouldn't have used that bright green, but that's all right. Okay, so a vertical asymptote is a discontinuity because my Domain has a break in it. Non-removable or infinite. Okay. Horizontal asymptote. What's my horizontal asymptote? Y equals 3. Now, I know we have the graph to look at. Fair enough. How do we know that horizontal asymptote? Remind me, just by looking at the equation.
That's what kills me.
Well, my hint would be to talk horizontal asymptote, I would come back here to the original equation.
Take the bottom.
No, that's your verticals.
Oh, yeah.
But if we look, and I'm not just talking about the bottom, I'm talking about the whole thing. Horizontal asymptote has to do with where the biggest power is. So in this case, so if the biggest power is on bottom, my horizontal asymptote is y equals 0. If my biggest power is on top, there is no horizontal asymptote. If the biggest powers top and bottom match, we use the coefficients. So the fact that it's 3x squared over 1x squared and the powers match, you're using the coefficients. So 3 over 1 or 3. Does that ring a bell?
Yeah.
Just exactly. Okay. That's all review technically, isn't it? I don't know. Something might have slid in there somewhat new, but that was pretty much review. So, okay, we're going to talk a lot about limit notations and how limits work, the basics in this lesson. So, we're going to revisit notation we learned in pre-calc. We need to convert these old methods of explaining extreme behaviors into limit notation for use in calculus. So it asks us to use the graph to complete the table below. So this is the same graph as earlier, isn't it? Okay. Now, we've talked about, and this isn't the exact notation we're going to use, but so as x approaches negative infinity, the graph of f of x approaches what? So as x approaches negative infinity, that's saying as we go where? Left. F of x approaches what? So that's saying your function, or that's saying your y value approaches what?
30.
Because what are we doing? We're looking right here, yes? As my graph goes left, as it goes infinitely left, what's that going to get closer to in terms of the y value? It's going to get closer to 3. Now, official notation, I'm going to write it right here. The limit as x approaches negative infinity of f of x is equal to 3. Okay, that's your official notation there. And that's what you need to be able to write and read and understand. And it's getting closer and closer to 3. It doesn't have to touch 3, but that's where it's aiming. Okay, what about over here? As x approaches in positive infinity, the graph of f of x approaches what? Yeah, so as we, wait, what did you guys say?
I don't know if the whole.
Well, it's as x approaches infinity. So as x approaches infinity, that's past the whole then, right?
Yeah.
So that means as we're going here off to the right, long term, where's that? What y value is that graph approaching? 3. It's approaching it from the underneath instead of the up above side, but it's still approaching 3. Official notation, the limit as x of x approaches infinity of f of x is equal to 3. Okay. As x approaches negative 3 from the right, the graph of f of x approaches You guys with them? So as x approaches -3, where's -3? That is this vertical asymptote, right? So as we approach from the right, so that's me following along over here. What y value am I approaching? We're just going infinitely down, so -infinity. Now, when we talk about official notation, I introduced this yesterday. The limit as x approaches -3 from the right means I'm going to put a little plus after the -3. And that's indicating we're not just approaching -3, but we're approaching from the right of f of x is equal to -infinity. As x approaches 3 from the left, read carefully there, as x approaches 3 from the left, the graph of f of x approaches
Wait, what?
as the graph approaches 3. So where is 3? 3 is over here, yes? So as we approach from the left, so that means I'm going to hop on the graph close to 3. So now, as I'm approaching 3 from the left, what y value am I approaching? I'm approaching the whole. What is the y value of the whole?
5/3.
5/3. Remember, it's from the other, it's the same graph as the other page. Okay? It doesn't matter that the graph doesn't exist at 5/3. It's approaching that value. That's what a limit is. A limit doesn't have to exist at that point. It just has to approach it. So now, how do I write this? The limit as x approaches 3 from the left means I'm putting a negative after the 3 of f of x is equal to 5/3. Okay? As x approaches -3 from the left, the graph of f of x approaches.
Positive infinity.
So -3, we're hopping on the graph close to -3. Now we're going up, and so that is indeed positive infinity. The limit as x approaches -3 from the left of f of x is equal to positive infinity. And then as x approaches 3 from the right, the graph of f of x approaches.
5/3.
We're back at that 5/3 because we're hopping on the graph to the right of 3 and close to 3. So as I approach 3 here, I'm approaching that whole. So the limit as x approaches 3 from the right, so plus f of x is equal to 5/3. Okay? We're going to practice a lot of reading limits, looking at a graph and understanding how to answer the question. Honestly, relatively easy, but it's the learning curve that you have to get past here. Okay? Easy once you understand it. Okay. Now, the question asks us, can you explain what the value of a limit represents in terms of the graph? Debating, I don't want to write as much as what I have in my notes. Thoughts here? What's the value of a limit represent in terms of the graph?
Represents asymptotes. Where the
represents where the graph is going, what you can't see.
Okay. What are we looking for here when we're looking for the value of the limit? What all these limits equal to are what kind of values? we were given x values, right?
Oh,
So as x approaches, as we're approaching some x value, where our answer is a y value, yes?
Mhm.
Okay, and that's important to remember there. Okay, so I have the limit as the y value that the graph is approaching from both the left and the right side of the target value, or x equals c. Asymptotes were mentioned. Holes were, the limit can also occur at a hole or approach an asymptote. Okay, so I'm going to keep it basic. The value of the limit is the y value. Okay. Limit can also occur approaching a hole or an asymptote. Okay. That's the other piece I guess I might say is that limit can also occur approaching a hole or asymptote. This is the one where. Okay, down there at the bottom before we turn to the next page. Okay, informally, a limit is a y value. Okay, that's what we just talked about, which a function approaches as x approaches some value. Now, notice it says down there, I know mine's kind of hidden down there, but the limit as x approaches c of f of x is equal to L, means as x approaches c, f of x approaches the y value of L. Now, something to keep in mind is that L represents a real number. Okay, now remember that has a place somewhere, but just to kind of remind you, L represents a real number. And I am too close to the bottom here. Okay. Okay. Ready for the next page?
yeah.
I like the next page. It's fun. Okay. So consider the function shown at the right. It's a nice one, isn't it? Okay. Nice broken up pieces of graph. Say you want to find the limit as x approaches 4. What's that plus sign mean? From the right of f of x. The positive sign in the limit notation indicates a right-hand limit. So that's why I always say from the right. It's a right-hand limit. If you think of the function as a highway and imagine you are traveling along the graph of f of x toward x equals 4 from the right, not to the right, but from the right, you stop at the vertical line x equals 4, the y value where you stop is 3. So therefore, the limit as x approaches 4 from the right of f of x is 3. So if we're looking for approaching 4, I don't care what the graph is doing over here. I care about what the graph is doing around 4. So I'm going to hop on the graph around 4. It said from the right, so I'm going to hop on the graph to the right of 4. And I'm just going to go up here. And as I hit the line 4, right, as I hit that line, what y value am I approaching, or what y value do I land at? And that is the 3. Okay? Now, we have a whole bunch of questions to answer here. Use the graph above to evaluate each of the following limits. Now, A, f of 2. Don't fall for it, you know it. Maybe you don't know it. What do they mean by f of 2?
Like y2. Like 2 of the graph. Does that make sense?
Isn't it?
Like that's a y value, that's what I'm saying.
So it's the y value when x equals 2. Okay, so when we talk f of 2, yes, this is a y value, and it's the y value when x equals 2. Now, so when you look at your graph and you find the 2 line, what is the y value of the graph at that point?
-1 because it's touching that.
Okay, so the answer is -1. And here's the deal. Is there a lot of quiet because there's 2 points there, kind of?
I was trying to remember which
Yeah.
one was touching.
So here's the deal. There's 2 circles there, but one of the circles is a closed circle. That means that is part of the graph. The other circle is an open circle. That means it goes all the way up to 2. So like from the right, it's going to 2.0000001. Okay, but it does not touch 2 from above.
Like a hole, kind of.
Or it does not touch, I'm sorry. Yeah, it does not touch 2. It's a hole at 1. Okay. Okay. Come on. So what's f of -1? Do you see it? If you look at, you want to look at the ordered pair -1, 2 and say 2, don't you? But the graph doesn't exist at the point -1, 2 because there's a hole. So that's a removable point. That y value up there is 4, and that's where the graph exists. Okay, let's try some limits. The limit as x approaches 4 from the left.
This is so hard. I'm bad at my left and right.
Do we need the L's put up?
I'm gonna write it on it.
Go for it. Put an L at the top on your left corner and then a right on the top of the right corner. Okay, so as we approach 4 from the left.
Positive infinity.
No?
3.
Or 3, yeah.
3.
3.
So as I approach 4 from the left, so x value of 4. As I approach that 4 from the left, so I'm going to hop on the graph over here. What y value am I approaching? 3.
Or limits, are we always doing y values?
Your answer is always a y value.
Yeah.
You're approaching an x, you're using the x to find the location, and then we want to give the height. Okay, we ready for D? As x approaches 2 from the right, what is the limit?
1.
Even though it's a hole, yes? Okay, so here's the deal. Because I know that hole is thrown. As we approach 2 from the right, so my graph to the right is here. What y value are we approaching? You're approaching the y value of 1. It's a limit. It doesn't matter if it doesn't exist. Okay, when we said f of 2, f of -1, it mattered if it existed. A limit, it doesn't have to exist at that exact point. It just has to be heading towards it. Okay? We're trying E. The limit as x approaches 2 from the left.
-1.
So approaching 2, so this time from the left, I'm going to hop on the graph here. What y value are we approaching? And that is a y value of -1. Okay. Stop me if I need to stop, otherwise I'm just going to keep going. Limit as x approaches -1 from the right.
4.
No?
2.
As we approach -1 from the right. So hop on this graph. What y value are we approaching? And we're approaching 2. It's a limit. It doesn't have to exist. You can approach holes. Okay? The limit as x approaches -1 from the left.
2.
Also 2? Because we're approaching the same point just from the other piece of the graph. Okay. As x approaches -4 from the right. So as we approach -4 from the right, we are at a y value or a height of 2 again, yes?
Mhm.
Yeah.
Okay. As x approaches -4 from the left, and no answer in calculus terms is D and E, does not exist. Okay, so why is this not existing?
Because there's no line.
Stops.
There's nothing to follow to approach. The graph just starts there, so there's no way to approach from the left. We can approach from the right, but we can't approach from the left because the graph doesn't exist. So our official answer in calculus terms is D and E, does not exist, there is no answer. Okay? Okay. J, the limit as x approaches -1. What?
2.
Now, we didn't say left or right, so what's that mean? You're approaching from both ways, and here's the deal. They have to meet. They have to meet at that same point, or we have a problem. Okay? As we approach -1 from both ways, did they meet? Yeah, and we could even go back and look. -1 from the left was 2. -1 from the right is 2. That means as x approaches -1 is 2. Okay? What about the limit as x approaches 2?
Can you have 2?
You cannot have two answers.
So then it doesn't exist.
So it doesn't exist. Because here's the deal. What did we know? As x approached 2 from the left, it was -1. As x approached 2 from the right, it was +1. As we approach 2, are we meeting at the same point?
No.
So when there's no left or right, they have to meet at the same point for the limit to exist. Otherwise, D and E. And that's because approaching 2 from the left was -1, and approaching 2 from the right was +1. That's why it's a D and E, because they met at different points. Okay? Getting the feel? Limit as x approaches 5.
Negative infinity.
Until we got down to 4.
What'd you say, Aiden?
Negative infinity.
No.
Can you pass that little break, or do you have to stop?
-2. I don't know.
So on the left side of the graph,
Yes.
okay, on the left side of the graph, we had a point here. At a point, you stop. On the right side of the graph, we have an arrow. So what's that mean that graph is doing?
It keeps going.
It's keeping going, like it goes on past that. So as we approach 5, you get on this line and you approach 5, are you approaching a point? Yeah.
-2.
You're approaching a point that has a y value of -2.
Oh,
I mean, in all reality, they're trying to trick us, right?
yeah.
Are we okay with that, though?
Mm.
Okay. What about the limit as x approaches 0?
-1.
Right? I agree. As you approach the x value of 0, you're going to land at -1, aren't you? The limit as x approaches 1.
-2.
It's just a regular spot on the graph, right? As you approach from both ways, you land at -2. Those are limits, guys. We've got to be able to do limits. Okay? Okay. Think about this. if we think of the function as a highway, then the point at 2, -1 could be considered the end of the road. There's 2, -1. Okay, end of the road, right? Which that end of the road was a closed circle, wasn't it? It was a filled-in circle. Well, the point at -1, 2 is more like a pothole. What's at -1, 2? A hole. Okay, so it's a pothole. It's a break in the road, so to speak. How would you describe the points located at? What would you say about 2, 1?
Like a pot. What?
I don't know.
Good circle.
Well, it's not. If I'm thinking pothole, the road continues on the other side of that pothole.
It's a cliff.
It's a cliff. Okay, I could go with cliff. I mean, based on what I have written in mine, which I probably took the idea that Jean had in her notes, but I have written down dead end without a barrier. Is that a cliff? In other words, the road just ends, but there's nothing saying stop here because it's that hole. Okay, so cliff, dead end without a barrier, whatever you want to think of it as. Dead end without a barrier. Cliff. I don't know. The idea is the road ends there. It doesn't just continue on the other side of that pothole or that break. There's a big gap. So the road ends there. And there's nothing saying, hey, stop here. There's no point in saying stop here. What about 4, 3?
The top of a roller coaster.
So we could talk top of roller coaster. If we're thinking of a flat road, though, we're gonna have
Stop sign.
Yeah, it continues.
yeah, it continues. I mean, that's the key. I have mine list. Mine is listed as bump in the road because it does. It continues. It doesn't continue in a, what do I want to say, a continuous fashion. You know, I mean, it connects, but it's, you've got to turn there or something. So
Detour.
I don't know.
Detour.
As I said, I didn't write these notes, so.
Detour.
Okay, just some ideas to think about. Okay,
Oh my God.
now we're going to go a little more formal with our definition.
Oh, yikes.
Why do I not even remember the bell ringing at halfway through class?
It
Oh,
did.
yeah.
We were like,
I must have been really
we were like
engrossed.
halfway through that probably.
Okay.
It's time to lift party.
I know, it always throws me.
What is
Okay. Okay, guys. Getting a little more formal. So, limits can fail to exist, and we've got 3 situations where we can talk about limits possibly failing to exist. As we look at this one, why does the limit not exist at x equals -1? And what's happening here?
There's, yeah.
And but not just a hole.
The cliff.
There's a break. There's a jump. There's, you know,
They're not
they are not continued. Okay. So at this point, this doesn't exist because you've got a different limit on the left, limit on the right. As we approach from the left versus as we approach from the right, you're approaching 2 different y values. So case number 1 is when limits differ on the left and right. Limits differ on left and right. Okay. And in terms of justification, write out your limits here. So if we look at the limit as x approaches, what are we doing? -1. And I'm going to go -1 from the left of f of x. So what's the limit as x approaches -1 from the left? As we approach from the left,
I was looking.
it's -1. Now let's do the other one. What's the limit as x approaches -1 from the right?
1.
There's the 1. Caitlin will learn her left and right in AP Calc, right? Now, how can we justify this limit does not exist? Because the left and the right-hand side do not equal each other. So I can say that the limit as x approaches -1 on the left of f of x does not equal the limit as x approaches -1 from the right of f of x. Okay, that is official AP language talk. Okay, if you have to state that a limit doesn't exist, this is the official way to do it, to say that the limit from the left does not equal the limit from the right. Because part of the definition of a limit is that the limit from the left equals the limit from the right. Okay, so little side note here, this is good AP vocab. Okay, that's good ways to write explanations in AP. Okay. Case 2.
What's even happening?
Okay, well, it's going up, down, up, down, up, down. So case 2, I'm going to call oscillating behavior. Because what's something mean if it's oscillating? Yeah, it's going back and forth, up and down. So, justify why the limit does not exist at x equals 0 for f of x equals the sine of 1 over x. Well, can you tell by looking at this graph? Not really. It's too much of a blur, if you ask me. So, let's graph it real quick. What is it? Sine of 1 over x?
Wait, how would you build these in?
There's a break.
What's happening?
And on just my regular Zoom screen, I can't tell anything, can I?
There's a break.
But if you start doing some zoom in, so hit zoom in, then hit enter an extra time, you're seeing some information there, aren't you?
Yeah.
Now, if you zoom in one more time,
I got one, yeah.
Oh.
that's like what that screen looks like, isn't it?
Mm-hmm.
Okay?
Mm.
The, let's say, I curved it. If you keep zooming in, how does it get? You eventually see, I think you have to zoom in.
They're just gonna explode.
Why does it like show more when you zoom in?
Because you're getting to where you can see more.
But fill the whole screen.
I'm just curious.
Oh, it's lagging.
Yeah, mine started to lag.
I was trying to do a Z-box.
It takes so.
Because you're zoomed in so far.
Maybe.
Yeah, Z-box doesn't even really do it. Well, it kind of does. I'm getting in there, you know. Now, I'm actually going to go back to Zoom 6 for a moment and actually probably just zoom in once. I mean, that kind of gives you an idea there. That's probably the best screen out of what we've seen to look at. Here's the thing. Remember if you hit trace, it's going to put you on the graph somewhere. And notice right here it's saying at x equals 0, my graph does not exist. If I go one click to the right, my graph is now up at 0.95. If I go the other way, one click to the left, my graph is at negative 0.95. So those are some ways that you can, use that to help you is by doing some trace. Okay, you just have to play around with the calculator, manipulate. So, justify why the limit does not exist at x equals 0. Interesting. On my notes, I wrote inspect negative 0.1 to positive 0.1. Ah. Well, even that makes it hard to tell, doesn't it? But, that gives you a little bit of an idea there. You saw it break if you watched it graph. Okay? So,
Sorry.
here's the deal. If we look at the limit as x approaches 0, if we look from the right, when we looked from the right, that graph was up high, wasn't it? Okay, so it was at like 0.95 or something, but I can also just specify it as that limit has a value greater than 0. Okay. Whereas, what about when it approached 0 from the left? It was less than 0, wasn't it? Because it was down at negative 0.95 or something like that. Okay, so this limit is greater than 0, while this limit is greater than 0, therefore we can say limit does not exist. Now, I just used the word therefore. I don't know if it comes up in any other classes. A little triangle of 3 dots is therefore. Okay, that's a current, common math. But we can say therefore the limit does not exist. Okay. And we have case 3. Now, case 3 is a difficult one for me, but this has to do with unbounded behavior, okay? Because that graph is going where? Infinitely up, okay? So case 3 is a special case, and I'm going to call it unbounded behavior. Justify why the limit does not exist at x equals 2 for this graph here. Now, what do you see happening? If we look at the individual pieces, as x approaches 2 from the left, where's the graph going? Infinity. As we approach 2 from the right, where's the graph going? Infinity. So, what would it seem logical to say? If they're both approaching infinity, the limit as x approaches 2 is infinity. Okay, because they're both going up to infinity. Now, that is honestly an answer we use a lot, is infinity. Okay, and I'm going to write that, but I'm also going to put an asterisk. By definition, you guys remember back a page or so where I said a limit must equal a real number. Infinity is not considered a real number. Okay, infinity is an idea, it's not a specific number. And so with that concept in mind, it's not going to equal a real number. Okay, so if someone wants to argue, well, this limit doesn't exist, it's just that it doesn't equal a real number. Okay, so, but I am going to put the limit as x approaches 2 from the left of f of x is equal to infinity, and the limit as x approaches 2 from the right of f of x is equal to infinity. Thus, we can say the limit as x approaches 2 of f of x, since it approaches the same thing on both sides, we can generally say that's equal to infinity then. Now, I'm going to put an asterisk and say, by definition, infinity is not a real number. It is a behavior. Okay, so By definition, infinity is not a real number. Okay, it's a concept. It's behavior. And if you recall, it had to equal a behavior or a real number. So that's one of those, come on, right? One of those little catches if someone wants to say that it doesn't exist. Okay? Okay. I had a feeling we wouldn't get to the last page, but that's okay. We are going to do the next last page, which is important. Okay? We did a lot with reading a graph. There are two key ways we get limit answers. We read graphs and we read tables. Calculus loves tables. Okay? So, consider the function f of x equals x minus 3 over x squared plus 2x minus 15. If we had a graph, it'd be easy to find the limit as x approaches 3. Right? You're looking from the left, from the right, and you're looking to see where they go. We don't have a graph, so we can use a table. So the idea here is that if we evaluate what the function is when x equals 2.9, so what am I saying that we would do? Plug it in, yes? You are confident to use calculator, so I can just tell you the value, right?
Sure.
Why am I doing it? Saving time. So 0.1265. Unless I copied it down wrong or something, okay? That's what you get when you plug in 2.9. 2.99, 0.125. 2.999, yeah, whatever. 0.1250. I don't remember what the other one has after it, but okay. You plug in 3. It doesn't exist. I think your denominator equals 0 though. Okay. 0.1249, 0.1248, and 0.1234. So, the idea, okay, the limit as x approaches 3 from the left. Where are we looking? Where are numbers on the approaching 3 from the left? Okay, that's the 2.999 numbers, right? So as you approach 3, this is approaching 3 from the left. What are we approaching? It doesn't exist here, but what are we approaching?
0.125.
Looks like that 0.125. What about as we approach from the right? So now we're approaching from larger values. So as x approaches 3 from the right, what is that approaching?
0.121.
Okay, 0.1429, or does it look like it could even, the way the trend is going, 1.25 or 0.125? Okay, and you could put either answer there really, but I'm looking at the fact that if the 9 rounds the 4 up to a 5, yes? Okay, so if the limit from the left is 0.125, the limit from the right is 0.125, what's the limit as x approaches 3? 0.125. So that's how you can use tables, is you can look at those different values there. Okay, now, I don't know if you figured this out or not, but what's going to be at this graph? There's a hole at this point. Okay, so there's a hole or a discontinuity, specifically a removable discontinuity. I should have said removable discontinuity, actually. Get that vocabulary back in your brains. Removable or point discontinuity. Okay. Let's look at the rest of this page briefly. By evaluating certain types of functions at a particular value, we may not necessarily have a sufficient understanding of the function's behavior at a specific point. This is especially true for rational functions that contain discontinuities. This is why the idea of the limit is important. Rather than just going directly to some x value using direct substitution, we can approach a point from either side to get to some sense of behavior in the neighborhood. So what's going on in the area of that number, or the neighborhood? Now, there's the arch support construction for the Hoover Dam bypass bridge. Those two pieces of the arch, they're following the same line, right? Even though that piece of the arch is missing, can we see where it's going to be? Okay, that's the idea of a limit. They're going to meet at that same point, okay? What else? With limits, we're looking at the y value the graph approaches, not the actual y value at the point. When finding limits, ask yourself, what is happening to y as x gets close to a certain number? Okay, you're finding the y value for which the function is approaching as x approaches c. Now, this limit existence theorem. I know, there's a lot of gibberish there, yes? But it's really what we've just done. The limit as x approaches a value exists only if and only if the limit as x approaches a value from the left equals the limit as x approaches value from the right, which equals some real number. Okay, so if they equal the left and the right, that's the idea that a limit exists. And I guess it's verbally down there as well. Okay. On the back, we've got most of this done. So, you know, I don't remember exactly what's on this back page to know if it's something I'm going to come back and worry about or not. But I do want you doing the homework. Okay? Do the homework. We may or may not come back. As I said, sometimes I come back to notes, sometimes I don't. It just depends on what's in there.
If the limit does not exist, it's because there's a polar aspect to it, right?
Or
Well, that could still be the limit existing. But if they're going different directions, like if they're not meeting at the same place,
Then it doesn't exist.
then it might not exist.
So if it meets at the same place, it exists.
A limit exists. It doesn't have to, there can be a hole there. Okay? There can be a hole there. So, okay, yeah. And what I have written on that next piece, in general, a function must approach the same y value from the left and the right. However, the y value may or may not be defined there. So, okay, I'll try and remember to get the answer key posted. There's a lot of limits. So while the homework seems like a lot, what do you got? 3 pages, 1 page front, back, and another page. Think of mind how quick some of this went today, right? So.